the next thing we want to look at then are transistors. We won't go into in any great depth, just to get, again, the flavour of it. What are they? Well, we're all familiar with them. They're just 3-pin devices. Mostly used a lot for audio amplifiers in your telly or whatever. And essentially, you've got 3 pins, but we use them mostly for switching purposes, to switch on LEDs, switch on relays, that kind of thing. What are the 3 pins for? Well, you could think of it as an electronic valve. Current, as you know, is electrons that flow from to a positive charge. So it's going to go from the 0 or try to go up to the positive and complete the circuit. And we can think of this pin coming in as a valve that regulates how much current it'll pass, maybe none, maybe all, maybe something in between. So if we change what's happening in this pin by small amounts, we can make it an audio amplifier. So a tiny amount of audio coming in here can result in a much larger amount of current flowing through there and a bigger audio signal to your speaker or headphones or whatever. If we completely drive it on, we get full current and it becomes an electronic switch. So how does this actually work? Well, we'll go back one step. We discussed under the basic electronics course the idea of diodes. We said diodes only pass current in one direction. If you try to reverse the diode, it blocks current flow. And it's using what they call a p-n junction. It's just silicon that is involved in a process called doping. In one case, you add that set of chemicals, in the other, that set of chemicals. The result is, with that kind of doping, the silicon ends up with more electrons that would normally be in that situation. So an imbalance, so there's a surplus electrons in that material. The p-type, when it's doped, is the opposite. It's short of electrons. It's out of balance to be short of electrons, and they tend to call them the holes. The atoms that are missing an electron are called holes. It's just a concept. So what's this got to do with anything? Well, a diode is simply getting 2 pieces of material, one p-type, one n-type, and put them into the one case. Right. If we connect a battery, which you wouldn't really do, you'd have an LED or something, wouldn't you, in circuit, but just look at that. Then the electrons on the right-hand side are attracted to the positive of the battery, whereas the holes, in other words, the atoms with no electrons short, want to get it from here. So they tend to both migrate to the sides, which inhibits a flow of current. Why does that happen? Well, you may have come across, we often say it, that a diode will always drop roughly 0.7 of a volt across it, sometimes 0.65, an ordinary silicon diode. Why does it do that? Well, when you put the n-type and p-type together, at the junction between the two, they try to get a balance. And the reality is they end up with a piece in the middle, which they call the depletion, depletion zone. The depletion zone. Right? You can see there, it's got a situation where the holes have been filled by electrons. The electrons have been filled by the holes, and we've got it in reverse. There's now an electric field that has to be overcome by at least 0.7 volts to get the current flowing again, because the electrons are now repelled by another electron. So they can't go across until they get forward biasing. So that's how a diode works. And we use the exact same principle there. If we put the battery the other way around now, we get electron flow because it's proper biased by enough voltage. We use that a lot. There's that little kit we have for the crack tester. If you put the power on one way, one of these diodes, because an LED is just a diode at the end of the day, right? One diode is forward biased and will illuminate. The other diode, by definition, because it's reversed, is going to be reverse biased. It won't light up. If you could invert the power to the track, the opposite happens. The other one now lights and the other one extinguishes. Right, so how does this translate into a transistor? I was just looking at the audience. Some of you are too young, but some of us are not. And we could probably understand an analogy of the old valves. I'm taking you back in technology to hopefully better understand the new stuff. What we've got here is just a glass tube, which is a valve, and you heat up the cathode. And as it heats up, it builds up a cloud of spare electrons around it. They've been ejected from the cathode, but nowhere to go. If you put a high voltage on the anode of a valve, that should attract them. But the gap there is too big for it to jump. It can't quite make it. It wants to go across, but it can't quite make it. So what we do is, if we apply a smaller voltage there, just enough to start the electrons moving towards that grid, they start moving towards the grid and discover, hold on, there's an even greater attraction up here. So by changing the voltage on that grid, we're allowing more and more current to flow. So the grid of a valve acts like a valve, if you like, to control the amount of current flowing. And that same principle applies to transistors. There's a whole range of different transistors I'm not going to go into today. We might make that the subject of one of the topics on another Sunday. We're looking at the most common bipolar transistors. It's come in two flavors. You've probably seen them called NPNs and PNPs. Always remember, if you're not sure which symbol represents which one, I always say if the arrow is not pointing in, it's NPN. That arrow is not pointing in, that must be an NPN transistor. That one is pointing in, must be a PNP. And what the NPN and the PNP mean is what's in the sandwich. The diode is one N piece, one P piece together. The NPN is a sandwich, two N pieces, two N types with a P type in the middle. And the PNP, whoops, over there is the opposite. You have one N type in the middle and two P types either side in that sandwich. And that determines how you get the current to flow. So if we think back on the valve analogy for a minute, the current would like to flow from there to the higher potential, can't quite make it. But if we get a small current flowing through the base, then once it starts to flow, it'll find a higher potential there and go up there. So we could put 5 volts on there, and we can put on a tenth of a volt there for talk's sake, 100 millivolts. And that's enough to get the current flowing that way. And once it starts flowing, it discovers an even higher potential that way, and it breaks down the barrier and current flows. And And a PNP is the current flowing in a different direction, obviously, but same principle. Look at a PNP. A lot of them use the BC547. It's a PNP type. The arrow is pointing in the way. So the current flows. The good way to remember it is the middle letter's N. So N means negative in this case. So a low voltage will make the current flow. So it's low voltage makes a current flow, high voltage switches it off. Right. If you keep reducing the current, you eventually get to a point called cutoff, where no current flows at all. The other popular transistor is the 547, and it's an NPN. In other words, to make it start to conduct, we want the base to be at a high voltage. So if there's no voltage on there, no current flows, if you increase the base emitter voltage, you'll increase the current up to a maximum that's allowable, that can stand. And decreasing it will cut it less and less current until it actually completely cuts off. I've got this board. I'll try and hold up and show you in a second. What I've got in it is my power coming in the bottom, connects across this resistor. If I pull that up and down, then what comes out of here will go between 0 volts and 5 volts. So I've got a spot here that goes between 0 and 5. If I take that to the base of an NPN, we can see what happens. If I take it also, that same one, to the base of a PNP, what happens? Right, let's see. As it stands, nothing. But what I'll do, I'm going to connect there, like I said, right, to the base. Yeah. When it goes high, can you see the LEDs illuminating? It is an NPN type, so going high should switch it on. It does. Going to 0 should switch it off. It does. If I then move that across to the other one, it's the opposite effect. Now going high switches it off, and going low switches it on. It's a PNP, it says, after all. In fact, if I then switch both of them at the same time, there we go. We can have one high and one low. If I take it off and put it on to this one, it's an NPN, if you can see it. It's just a high power light, and I'm using a high power driver transistor, so an NPN type. So NPN, positive makes it conduct, on, off, on, off. So there's no magic in it, but it does have certain characteristics we'll look at next. Yeah, that was just what I showed you essentially. That's all I did. High turns on an NPN, a low turns on a PNP. what can we expect from them? Well, there's two factors. One's called gain and one's called saturation. So the gain just says, if I put in X, what can I expect out? If I have 1 milliamp between the base emitter, do I get 20 milliamps at the top or 100 milliamps? What's the factor that it multiplies by? And you can see there, a BC547, usually a gain of 500, although they can get them, there's a range of them, but let's look at a typical 500 gain. That means if you want to switch, if you only allow 1 microamp between the base and emitter, you get 500 microamps out. If you put in 200 microamps between the base and emitter, you get 100 milliamps out. So you can see, you only need a very small amount of current to flow to allow you, that would be happily drive an LED, for example. So a tiny input current can drive an LED quite happily through a transistor. And that's called the gain. But you'll see we get to a point here that this particular BC547 can only maximum output 100 milliamps. So you can keep on adding here till you get to the 100 milliamps. But if you're trying to pass even more current, there's no change. You get to the point what's called saturation. You've got as much out of that transistor as you can hope for. In an audio setting, that's called overdrive. And you end up with terrible distortion in the audio. You've probably all heard that if you turn the volume up too much in some of the speakers or audio amps and so on. If you overdrive a circuit, you go into saturation. In other words, it can't swing, stop swinging. You've reached a peak where it can't output any more current, even if you tried. So that's the very well-known and well-used 547. I also showed you operating the brighter light, TIP122, which is a power transistor. And they vary. That one can go up to 5 amps. The BD237, however, has got a very low gain, 250. So if you want it to operate a solenoid at say 2 amps, you have to put 8 milliamps between the base emitter. Having said that, we're getting a very small input, allowing a very large output to happen. You can call it, if you like, a current amplifier. The small change here means a very large change there. We use that a lot because, for example, PIC chips and Arduinos have got output pins. Somebody trying to join us. And the output pins of a PIC aren't able to drive a large relay, for example, or that large bright light directly. It may be only allowed to have, say, 25 milliamps maximum current out the pin. And that's why you'd be using one of these to boost the current. So you'll see quite a lot, including the one I just did, the Shuttle Plus. You'll remember in between the PIC and the relay was a transistor, and its job was to take the small current changes come out the PIC to switch the larger current required to operate the relay. There's a spec for the 557, and you'll see along the very end here, that they're not precision components. You'll see there, the BC557 has got a maximum gain of 800, but they only guarantee a minimum of 125. There's quite a range. And 5557B, 5557C, again, different ranges, but they're all ranges. And they tell you the maximum current you're allowed. So you can look at the spec and you can actually calculate what you need in a particular situation. There's a 237, which is the high power one. And again, you're not expecting much in the way of a gain from that. You'll see that the current gain here is a way down to, could be as low as 90 or even 18, but maximum of 260. So the higher power ones need a higher drive. That's why you'll sometimes see a high power transistor being actually driven by a smaller transistor. So the low current drives a small transistor, which can then drive a higher current into this one, which can then drive an even higher current. So you can tandem them up. You'll find them in pairs. There's a very simple example you can even try. I did say that you only require a very small amount of current. That circuit, if you put your finger between the base and the positive and 9 volt, then even the amount of current going through that finger is enough to allow the current to go from the emitter to the collector. Tonight, try it and just see for yourselves. How do we use it? Well, that's an example. We've got the LDR train detector. And what we're doing is, we've got across the 12 volt supply, we've got a light dependent resistor and other resistors. So that point pointed to by the arrow, its voltage will change. As the light value changes on there, that resistance changes. And that's the equivalent of a potentiometer where you're moving the center up and down. And that will then decide the switching point to bring on the transistor. You'll notice that when we do that, have I got one here? Yeah, let's see. I'm covering up this LED, LDR rather, and you'll see the LED on the right changing. But what it's doing is, it's not fully switching on, it's fully switching off. There's intermediate, I don't know if you can actually see it, intermediate amounts of illumination coming out. Because we're in that zone where it's a current amplifier. So the amount of current that's flowing through this piece here is increasing the current flowing through there up until you get to the point of saturation. If I fully cover that, then we saturate this diode, the full current that it can pass will be passed. So we use that principle there for the LDR TOTI. That's the logic tester. If you want to find out if a point is at 0 volts or 5 volts, then you want one lead to light or the other. So all we do is we use a PNP and an NPN. So when one's high, it'll switch one off and the other on. Then that same probe goes to a 0, it'll switch the other one on and the other one off. So any one point, it'll switch one or the other. If the probe's going nowhere, then you don't get any of these to light brightly. You only get one of these to light up when you actually touch a 0 or a 5 volt supply. The idea being by that, by the way, is that you can then tell the difference between 0 volts and just a broken wire. If you go to a point with your probe and you get a light lighting up, that shows is at 0. But if nothing lights up, there's no potential at all, 0 or 5. There's just nothing on. It's a wire that goes nowhere, or it's a chip that's blown and there's no output and so on. So it's used for logic tests to give you a positive for 5 and also a positive for response for 0.